So before going further, let us revise what we have discussed in yesterday's lecture. So we were talking about generalized heat conduction, one-dimensional steady-state heat conduction through fins. And yesterday we have derived the equation or temperature distribution equation for case number 2, that is fin, that is heat dissipation from a fin of finite length with insulated at the tip. We had considered a fin of finite length L, which is insulated at the tip. And for this boundary condition, we could derive this temperature distribution equation, this theta x over theta s is equal to cos of hyperbolic ml minus x over cos of hyperbolic ml. And we could also calculate what will be the rate of heat transfer from this fin if it is attached to the base surface with insulated tip. Now let us move further. Let us discuss case number 3. So case 3 is heat dissipation from a fin of finite length losing heat at the tip. So let us draw the schematic for this. Let us consider there is a fin of some finite length. It is attached to the base surface having temperature Ts. It is exposed to the environment having temperature T infinity. By virtue of conduction through the fin material in the x direction and heat transfer from the fin surface due to convection, temperature of the fin will be diminishing in the x direction. Now let us draw its temperature variation. This is the temperature variation in the x direction, and this is the x distance. Temperature of the air will remain constant. It is not going to vary at all. Temperature of the fin at x equal to 0 will be equal to Ts, isn't it? And it will go on decreasing in the x direction. So this is nothing but Tx, variation of Tx. Now what is happening actually here, what this boundary condition is all about, the fin is attached to the base surface of some finite length L. So this boundary condition means this is x equal to L at this point. Now what is happening at this tip? lot of disturbances are created by these latecomers in the real world as well as digital world. So what is happening at this tip of the fin, that is at x equal to L, heat is conducted and heat is convected. And since we are considering steady state, the rate of heat conduction will be equal to rate of heat convected out of the fin at the tip of the fin. This is actually the case number 3. Title of this figure will be Heat or fin losing heat. Now, let us enlist the boundary conditions for this case. Now, let us try to figure out all these 3 different cases. In case 1, what we have discussed, what was the boundary condition? There was a fin of infinite length, infinity. So if that fin is attached to the base surface, how temperature distribution in that fin will be varying? So we have, and what will be the rate of heat transfer from such fin of infinite length? So for this case 1, we could derive temperature distribution as well as rate of heat transfer. In case number 2, there was a fin of finite length L, but it was insulated at the tip. So for that case as well, we could derive temperature distribution as well as rate of heat transfer from that fin. Now case number 3 is heat dissipation from a fin of finite length losing heat at the tip. So if I consider this point, into this side, left hand side, heat will be conducted, and from the right hand side, heat will be convected. And since we are considering steady state, both these rates will be same. So boundary condition number 1 will be at the root of the fin. Root means at this point. So at this point, what we are considering, temperature variation or temperature of the fin will be surface temperature at x equal to 0. In terms of excess temperature, I can also write it as Tx minus T infinity is equal to Ts minus T infinity, or theta x is equal to theta s. This is the boundary condition number 1. In fact, boundary condition 1 is always going to remain same for all the 3 cases. Now boundary condition 2, what is happening? At the tip of the fin, that is at x equal to L. What is going to happen? Rate of heat transfer by conduction is equal to rate of heat transfer by convection. Since we are assuming steady state heat transfer, let us write down the equation for rate of heat transfer minus K. What will be the area normal to heat transfer? If this is the fin and this is its cross section area, for time being I am taking it as a rectangular. So what will be area normal to heat transfer? This will be cross sectional area. Temperature variation dTx over dx, and this entire rate of heat transfer I am considering at x equal to L. So this is the rate of heat conduction into the fin at the tip. Now Rate of heat convection from Newton's law of cooling, H into surface area into Tx minus T infinity. That is also at x equal to L. Now we know, see, this is the tip of the fin. Cross-sectional area normal area normal to heat transfer for conduction will be cross-sectional area, and from the same area heat transfer by convection is also taking place. So what actually the conclusion is, at the tip of the fin, that is at x equal to L, cross-sectional area of the fin is equal to surface area. So this will get cancelled. So it will become dTx over dx at x equal to L. AC has got cancelled with AS. I can write it as T into Tx minus T infinity over minus K at x equal to L. Got the point? This is second boundary condition. Now, if I take into consideration that x equal to L, it will become dTL over dx, because at x equal to AL, Tx will be TL. If it is to be calculated, and minus H TL minus T infinity over K. In terms of excess temperature, this will become d theta L over dx is equal to minus H. I can write this difference in terms of excess temperature as H theta L over K. So this is the boundary condition number 2 in terms of excess temperature. In every case, we need two boundary conditions to get the values of constants C1 and C2. Correct? Okay. Now recall equation number 7. What is equation number 7? If you don't remember, let me get back to you to equation number 7. This is the equation number 7. So let us rewrite it once again where it is required. Equation number 7 is nothing but theta x is equal to, this can also be written as Tx minus T infinity is equal to C1 e to power mx plus C2 e to power mx. Now let us put these two boundary conditions into equation 7. So if I put boundary condition 1 and equation 7, what I will get? What is boundary condition number 1? At x equal to 0, theta x is equal to theta s. Here we go. So with boundary condition 1 and equation 7, left hand side will become theta s and right hand side will become C1 e power m0 because x is 0, c2 power minus m into 0. And this will become c1 plus c2, or theta s is equal to c1 plus c2. Let's say this is equation number A. Similarly, boundary condition 2 and equation 7. Now boundary condition 2 is in the form of derivative. Okay, so first I have to get this expression at x equal to L. So at x equal to L, theta x can be written as theta L. So equation 7 becomes, if in equation 7 I put x equal to L, so theta x will become theta L. Theta L is equal to C1 e to power ml plus C2 power, this is minus, sorry, this is minus ml. Okay. Now if I take its derivative, d theta L over dx, so what it will become? M into C1 EML plus M into, sorry, M, it is M into C2 minus ml. And this M will be actually minus from the law of differentiation. But just now I have seen d theta L over dx is equal to minus h theta L over k. So I can substitute here minus h into theta L over k. Let me take m as a common. C1 e to power ml minus C2 e to power minus ml. What I have done so far, I have found out the boundary conditions for case number 3. Then I am putting those boundary conditions 1 and 2 into equation 7. So right now I am simplifying. I am solving boundary condition number 2 and equation 7 simultaneously. So after solving this, I got this expression. Okay. Also, now let us do two things simultaneously. First, transfer this m on the left hand side and let us put the value of theta L from this equation. See. So minus h over mk, and let us put the value of theta L from equation C. It is nothing but C1 e to power ml plus C2 e to power minus ml is equal to C1 e to power ml minus C2 e to power minus ml. Okay, let's say this is equation number B. Oh, please do not change the order. This is equation number B. and this is equation number C. Otherwise, you will get confused. And the value of theta L I have got from this. So now I have equation A and equation C. And from these two equations, now I can get the value of constants C1 and C2. So it will be a laborious task. Okay. Once again, let us refine this. C1, I interchange the sides of this equation number B minus H over mk C1 e to power ml plus C2 into e to power minus ml. And this is equation number C once again. Now solving equations A and C to get value of C1 and C2. So let us do this exercise to get the value of C1 first. Now I can put the value of C2 into equation C from equation 1. What is that? C2 can also be written as theta S minus C1 into equation C. So C1 e to power ml minus, I am putting the value of C2 from equation A, that is theta S minus C1 e minus ml, and right hand side is minus H over mk C1 e to power ml. Now little bit algebra here, no engineering. Your mathematical skills will be tested here to deal with the variables. What I did, I put the value of constant C2 from equation A into equation C only. Now let us rearrange this. C1 e to power ml minus theta S into e to power minus ml. This minus minus will become plus C1 e to power minus ml. Similarly, on the right hand side, minus H over mk C1 e to power ml minus H over mk C2 e to power ml. Now let us take the terms with the same value of C1 and theta S. Oh, here also I need to put the values of C2. So let me correct it. I have the option to correct it. Theta S minus C1. Or let me correct it. Let me correct the entire term. So minus H over mk C1 e to power ml, and this will be theta S minus C1 e to power minus ml. So it will become a little bit lengthy. Now let us multiply minus H over mk C1 e to power ml. See, now I am multiplying minus H over mk and this term simultaneously. So minus H over mk into theta S into e to power minus ml Now next is minus minus will become plus h over mk c1 into e to power minus ml. Now let us take the similar terms on the one hand. So as you can see here, c1 e to power ml, c1 e to power minus ml. I write them simultaneously. Why I am writing this? Because we have some formula for this type of representation in the form of hyperbolic functions. Okay, then let me take h over mk yes, I take this term and this term with c1. So c1 is h over mk and c1 is common here. And after taking on the right hand side, this minus will become plus, this plus will become minus. So plus c1 is also constant, h over mk is also constant. So this will become e to power ml minus e to power minus ml. Let us say this is left hand side. Now let us combine terms with theta s. So it will become theta s, this theta s into e to power minus ml, and this term minus h over mk e to power minus ml. Got it? So we could arrange all the terms simultaneously. Nothing engineering. Again, I am saying it is algebra. Once again, C1 is common here, so I will take it out. What else will remain here? C1 is constant, and this will become e to power ml plus e to power minus ml. This is first term plus h over mk e to power ml minus e to power minus ml. This is the left hand side, and right hand side e to power minus ml is common, so I can write it as theta s into e to power minus ml 1 minus h over mk. This is right hand side. But I am interested to know the value of constant C1. So rewriting it to get the value of constant C1 will give me theta s into 1 minus h over mk. This is right hand side multiplied by e minus ml. Entire left hand term will go into the denominator, e to power ml plus e to power minus ml. This is first term plus h over mk e to power ml minus e to power minus ml. So this entire term represents the value of constant C1 in terms of known values of M and L and H and K. Everything is known. That is why C1 can be calculated easily now. Now let us find out the value of C2. So from equation A, what is that equation? Theta S is equal to C1 plus C2. So C2 can be written as theta S minus C1. Let us put the value of C1 here, theta S minus theta S 1 minus H over mk e to power minus ml over e to power ml plus e to power minus ml. This is actually in this fashion, please, otherwise you will get confused. Let me write it in a proper manner. This creates lot of mistake. So theta s minus entire this term, entire numerator and denominator, h over mk e to power ml minus e to power minus ml. So let us simplify this. Simplification will give me the value of C2. So what I am doing now, see, I will multiply this entire term with the theta s, then I will multiply this theta s along with these different terms. So let us do that two activities simultaneously. Theta s into e to power ml plus theta s into e to power minus ml plus theta s into h over mk e to power ml minus theta s into h over mk e to power minus ml. Then minus theta s e to power minus ml, and this minus minus will become plus theta s. I want to move in the right hand side, theta s into h over mk e to power minus ml, and entire to this numerator will be denominator, e ml plus e minus ml plus h over mk e ml minus e to power minus ml. So this way we could simplify this. Now let us find some terms will get cancelled. So see, this will get cancelled. Theta s e to power minus ml. Anything else will get cancelled. Minus theta s h power mk e to power minus ml. This will also get cancelled. So what will remain? Theta s is common everywhere and ml is common everywhere. So I can write it as theta s 1 plus h over mk e to power ml over this entire term. I know you are getting bored because algebra is nothing but jargoning of some mathematical terms. So EML plus E minus ML plus H over MK e to power ML minus e to power minus ML. This is the value of constant C1 and C2. Unless you do it, it is difficult for you to follow me. But okay, so this is the value of constant C1 and C2. Now putting the value of C1 and C2 into equation number 7, because we want to calculate value of Tx at any distance x along the length of the fin when under the boundary condition when fin is of finite length and losing heat at the tip. So see, it will be a big term. Theta x, the value of C1 is, what is the value of C1? Let me, okay. Theta s 1 minus h over mk e to power minus ml. This is the value of C1 and e into e to power mx. Because what is our equation number 7? Theta x is equal to C1 e to power mx plus C2 into e to power minus mx plus theta s into 1 plus h over mk e to power ml into e to power minus mx. And denominator is common to both the terms. So I am writing it commonly. Plus h over mk e to power ml minus e to power minus ml. Okay. Let us simplify this. So e to power m l minus x and e to power minus m l minus x. This way we can solve it. This will become e to power m into l minus x. This will become e to power minus m l minus x. In this fashion, I can write it. And theta s is common everywhere. So I take it on the left hand side. So it will become theta x over theta s. Now how it will become? See, e to power m l minus x, e to power m l minus x. From where it came? It came from here. After multiplying with this term. Plus e to power minus m l minus x. Okay, if I multiply this entire term with 1, I will get this. If I multiply this entire term with 1, I will get this term. Plus h over mk is common everywhere. Similarly, it will become e to power m l minus x minus e to power minus m l minus x. And on the denominator, e to power ml plus e to power minus ml plus H over mk e to power ml minus e to power minus ml. So this is quite lengthy term. Let us convert all these terms in the form of hyperbolic, cosine and sine function. So this will become e to power ml minus x plus e to power minus ml minus x. This will become twice of twice of cos of hyperbolic m l minus x plus h over mk. This will become sine of hyperbolic m l minus x, and this will be twice. Why twice? I will explain just now. This will become twice of cos of hyperbolic ml plus h over mk twice of sine of hyperbolic ml. Now, why I am writing in this fashion? 2 is a common here. First, let me simplify this. Theta x over theta s. So it will become cos of hyperbolic m l minus x plus h over mk sine of hyperbolic m l minus x over cos of hyperbolic ml plus h over mk sine of hyperbolic ml. So, and theta x can also be written as tx minus t infinity, and theta s is ts minus t infinity. Okay, where from where this has come, cos of hyperbolic mx is nothing but e to power mx plus e to power minus mx by 2. So from this I will get this. Similarly, sine of hyperbolic mx is nothing but e to power mx minus e to power minus mx by 2. So these are the formula we have used to convert this e to power mx term into hyperbolic functions. So this equation this is nothing but temperature distribution equation for fin of finite length and losing heat at the tip. A big derivation actually. So let us take a break for 5 seconds. I also got tired doing so many algebra. So in examination, generally this case number 3 is not asked, but we can't say anything. We must be prepared. So you can do this derivation for case number 3. That is fin of finite length and losing heat at the tip by convection. Now after finding out this temperature distribution, let us find out heat transfer rate. That is, if such type of fin is attached to the base surface, what will be the rate of heat transfer from this fin? So from Fourier's law of heat conduction, once again, minus KAC dTx over dx at the root will be x equal to 0 means root of the fin. That is the area where fin is attached to the base surface. So at root of the fin, whatever heat is being conducted, that is the rate of heat transfer from the fin. So let us find out this expression as well. Q fin is equal to minus KAC. And how can you find out the Tx from this expression? Tx will be this, I have to multiply this Ts minus T infinity along with this entire term plus T infinity. So Tx will actually become d over dx T infinity plus Ts minus T infinity cos of hyperbolic m L minus x plus h over mk sine of hyperbolic m L minus x over cos of hyperbolic ml plus h over mk sine of hyperbolic ml. Big term, requires lot of efforts for me to write. Now if you differentiate it, what you will get? Let me directly write you this value minus Kc. After differentiation, the first term will become 0 plus denominator will remain as it is because it contains no x word. Okay. So cos of hyperbolic ml plus h over mk sine of hyperbolic ml. Differentiation of cos hyperbolic ml minus x will become sine of hyperbolic m L minus x. Then we have to differentiate of this term L minus x. It will give me minus m. Similarly, h upon mk is constant. Differentiation of sine h m L minus x will give me cos of hyperbolic m L minus x, and differentiation of this will give me minus m. Simple rule of differentiation. Now minus m is common. If I take minus m, and this entire term is to be considered at x equal to 0. So let us put x equal to 0 in this term and simplify. Minus m is common everywhere, I can take it out. Minus will become plus. So it will become minus KAC m Ts minus T infinity. And after putting the value of x here, it will become sine of hyperbolic ml plus h upon mk cos of hyperbolic ml. And on the denominator, it will become cos of hyperbolic ml plus h over mk sine of hyperbolic ml. I can also simplify this as KAC m Ts minus T infinity 1 plus, wait, do not get impatient. I am just finishing it. My battery is also going. Just minute, just one line, then I will finish. One, uh, oh, sorry. KAC M Ts minus T infinity. So 1 plus, sorry, 10 hyperbolic ml plus hyperbolic of h upon mk plus 10 of 1 plus h over mk 10 of hyperbolic ml. So this is the rate of heat transfer from the fin of finite length. So this is case number 3. It is quite a lengthy case. So many hyperbolic terms are involved. Okay.